Okay. Okay. Then thanks for the thanks to the organizer for the invitation to this very interesting conference. And so we today would like to tell you a little bit about multi-messenger opportunities with massive black hole binaries. So we heard very interesting things that we can do in the high frequency regime of gravitational waves with neutron star binaries from both from Giancarlo and from Tanya. And so I would like to continue this overview, let's say, by moving to the high mass range and see what we can do. Hopefully, what we can hopefully do in the future when gravitational wave observation of massive black hole binaries will become available. So I talk a little bit about the dynamics, the formation and dynamics of massive black hole binaries, motivating why those are interesting sources for gravitational wave and electromagnetic radiation. And then I will touch a bit on the two, let's say, probes that we have or we will have for those sources, which are the laser interferometer space antenna and pulsar timing arrays. And I will try to flesh some ideas of making multi-messenger astronomy with those detectors, let's say. So first of all, let's start with some observational facts. And the observational fact I'm referring to is that when at the center of massive galaxies, there are massive black holes, right? So every time we had the capability of piercing through the center of galaxies, we found a massive compact object, and these massive compact objects we identify as a massive black hole. So most notably, we have Sagittarius A star in the Milky Way, the massive black hole in M87 that has been nicely photographed recently. And we know that these massive black holes are the central engines of quasars that we see shining at redshift 7. Okay, so supermassive black holes are in place already where the universe is very young, and the formation and evolution of these objects has very important consequences for gravitational wave astronomy. And if I have to sketch the structure, our understanding of structural formation in a nutshell, is that this proceeds in a hierarchical fashion. So you see here what we call a merger tree. So the progenitor history of a massive galaxy, the big dot here at redshift 0, which is decomposed in its progenitor at high redshift. So each massive galaxy we see today grows via a series of merger and accretion events from the assembly of less massive galaxies. Okay, so we also see that at the center of these galaxies there are supermassive black holes, and their masses correlate with the properties of the host galaxy, in particular the bulge mass and the velocity dispersion. Okay, so since the process is hierarchical, the process of galaxy formation, is also legit to think that the process of massive black hole formation is hierarchical. So you have some seed black hole in proto-galaxies at high redshift, and during the hierarchical assembly of galaxies, these black holes, following galaxy mergers, they sink to the center of the merger remnant. They form a binary that will eventually coalesce emitting gravitational wave. In the process, they will accrete matter, and so you will grow through a series of accretion and merging events, so the supermassive black hole that we see today in galaxies. Okay, but we don't know. So in this scenario, massive black hole binaries will inevitably form, but we don't know too much about them. We don't know exactly the nature of their seeds. We don't know how they grow exactly along the cosmic history, what their interplay, their feedback on the galaxy formation process, and simply because we don't have much observations of these objects at high, especially at high redshift, right? So, but the important thing for gravitational wave emission is the dynamical phase of those objects. And I will just sketch that out using this diagram that shows the time scale spent by two massive black holes following a galaxy merger at a given relative separation. So you see the parsec scale on the x-axis. Okay, so at the beginning, after a galaxy, when the two galaxies are in the process of merging, like in the top corner here, the two black holes find themselves at kiloparsec separations, right? And then they have to make all the way through essentially, milliparsec in order to merge because of gravitational wave emission. And to do that, these black holes go through several different stages. So there is a first stage where the two black holes don't know about each other, okay? And they evolve let's say individually within the within the potential within the ambient of the merged galaxy, right? And this is where dynamical friction is important. And this is my simulation of a massive black hole embedded, so in the outskirts of a massive galaxy. There is a massive black hole that is circling around. Because of gravitational pull, essentially the black hole deflects the stars that are surrounding him. And this causes this friction that pulls the black hole and breaks it down so that the black hole will eventually merge, as you can see in my very sophisticated simulation here. Okay, so this is the simulation. Well, you can do something much better than this. And on the right-hand side of the slide, you can see some actual simulation of this process happening in a stellar-dominated and in a gas-dominated environment. But the idea is that this process is very efficient to make black holes sinking to the center of galaxies. Okay. At that point, however, when they are both there, the two black holes start to feel each other's gravity. And so they sort of decouple, so to say, from the environment, and they form a Keplerian binary. And, you know, for reasons that I'm not following up here too much, dynamical friction ceases to be efficient when you have a bound binary. Okay, it becomes a perturbation of the central mass of the binary, essentially. And at that point, you need to rely on other physical processes to shrink the binary, because you are, when the binary form, you're still at parsec separation, and gravitational waves emission is not efficient at that separation. You need to bridge these 2-3 orders of magnitude in separation in order to coalesce because of massive of gravitational wave emission. And then to do that, you rely on the fact that your massive black hole binary is not in isolation, but is in a very dense nucleus of a merged galaxy. So it's rich of stars around there and potentially of gas. Okay, and it's being demonstrated by several authors that either ways, you know, with stars or gas, both stars and gas might be efficient in shrinking the binary. Okay, so for example, with stars, the idea is that if you have a tight binary, you have a small star that intersects the orbit of the binary, and in the chaotic interaction, the small stars acquires a high velocity and is kicked away. So this is the slingshot effect. Now, the star is small, you take away little energy from the binary, but if you repeat this process millions and millions of times, then you can significantly slowly shrink the binary. And this process has been demonstrated to, you know, be able to shrink the binary in timescale that can be of the order of hundreds of millions of years. Okay, so the binary, you can bridge this gap here, but the timescale of the binary become pretty long. And in principle, they can even stall if neither gas or star are efficient enough to shrink the binary. Okay, but when you reach the milliparsec separation, then gravitational wave emission takes over. And then we know that, you know, merger at that point is guaranteed. So you see, we expect these timescale here on the y-axis, they are pretty long. So they can get to, you know, 10 to the 9 to 10 to the 6 years, right? So we expect these binaries and these dual black holes to be everywhere in the universe. Do we see them? Well, the answer is yes and no. You know, it depends pretty much on what separations you are considering. So for example, at kiloparsec separations where we can actually resolve individually two accreting black holes with our instruments, it's actually relatively easy to find dual AGNs, right? So these are two accreting black holes in the early phase of a galaxy merger. Okay, so we are like here in the first phases of galaxy merger where we are at kiloparsec separation. As you move to lower separation, then it becomes more and more difficult to isolate the two accreting black holes like in imaging, right? And the best you can do is with the high resolution radio observation at parsec scale. And in fact, this object here, which has two flat radio cores, C1 and C2 here at 7 parsec relative separation, is the best, this object is the best, let's say is the closest relatively secure binary system that we have. And it's a projected separation of the order of 7 parsec, okay? If you go to lower separation, you need to rely on other things like spectroscopic signatures or timing signatures related, for example, to the variability of the source, because one can think if you have a binary the binary nature of the system introduces a natural period in the system, so there might be a natural periodicity related to the period. So there has been a number of candidates that have been proposed, both from spectroscopic and from timing signatures. But those are far less secure, right? Because there are other ways to interpret these things, okay? So we don't see many, let's say, tight binaries, but there are good reasons for for that. And the reason is that they are hard to find and we don't quite know exactly how they look like, okay? But those systems are strong emitters of gravitational waves. So in the future, we will be able to probe them both at the milliards regime with LISA, I should drop this from my slide, and at very low frequency with pulsar timing. So most of these, the rest of this talk will be devoted to these two, let's say, probes and how we can combine them with electromagnetic emission, okay? So first of all, LISA is, as you probably know, is the laser interferometer space antenna scheduled to be launched by the European Space Agency in the early 30s. And it will survey the gravitational wave frequency space in the milliards, okay? Which is anticipated to be the richest frequency band for gravitational wave sources. In particular, this is optimally placed to see the finite spiral merger and ring down of massive black hole binaries, okay? And, there is a very large community of more than 1,300 scientists working on LISA. If you're not part of it yet, please look at it, because it's a very interesting and it's a very nice community. And the one plot I want to show about LISA capabilities is this one, which is not even for LISA, it's for a scaled version of it. So take it with a grain of salt, but in any case, this plot shows essentially contours of signal to noise ratio for massive black hole binaries with the mass that you see on the x-axis in log scale at the redshift that you see in the y-axis. So for example, a Milky Way black hole at redshift 4, you can see it with with SNR of several hundreds, okay? And so you see with LISA, you can see supermassive black holes essentially everywhere in the universe, from few thousand to few tens of millions solar masses. And the lines that you see cut into this plot are examples of evolution of massive black holes, okay? And each dot is a merger. So it doesn't really matter whether you take a Milky Way-like black hole like the one depicted by the green curve, or a quasar at redshift 2, or quasars at redshift 6. All of them have cut through the LISA range in their lifetime, and most of their merger events that they experience are going to be caught by LISA, okay? Now, LISA will see these systems with ISNR, but do they emit radiation? Probably, but we don't have, let's say, solid modeling of this process, right? So the initial idea that, in the old-fashioned idea was that this binary is going to open a cavity, the quadrupolar torques of the binary are going to open a cavity in the disk. So this cavity will prevent material from being accreted, so those systems might be quiet. However, hydrodynamics and MHD simulations have shown that material can efficiently flow through the cavity and can be accreted onto the binary all the way through almost the merger, essentially. Other simulation of merging binaries in different environments have shown either an interesting flare happening at merger or some variability, but with not so much clear signature. Other simulations have found launching of jet be prompted by merger. But there is a lot of work going on, and this is certainly not a comprehensive list of authors for this very, very difficult work. But we can put together a sort of sketch whereby you have a merging binary that is spiraling, and during this spiral is accreting material, very likely in a periodic fashion. So there might be clear periodicity of accretion and perhaps luminosity during the spiral. Then since at the very final end, at the very end of the spiral, the massive black hole binary shrinking becomes so efficient that it leaves behind the disk, the luminosity might decrease perhaps toward the final merger, and then there might be a rebrightening post-merger. What really happens in this middle phase is essentially unknown, and as I said, it's a very exciting area of research. But it would be interesting if there is, for example, instead of decreasing a merger, there might be squeezing of gas in between the two holes, so you can have, for example, a flared merger. Okay, those things need to be, studied in more detail. So if there is a significant emission, we can try combine, for example, LISA with other probes. And in particular, here I will focus on Athena because there is an ongoing targeted work in that direction. And I will also mention the Vera Rubin telescope, LSST. So Athena is another large mission of ESA schedule that is covering the L2 schedule. So it will be launched possibly in the late 20s, perhaps early 30s. So the idea is to have Athena and LISA overlap at least for some years. So to have in the sky at the same time both the best low frequency gravitational wave detector ever made, well, actually the only one, and the best X-ray telescope that you can build. Okay, so the field of view of Athena is 0.4 square degree essentially, which is quite large, so it can actually pinpoint the sky localization of the gravitational wave source, depending, of course, of the parameters of the sources. And we will hear more about sky localization of gravitational wave sources from Sylvain and from Alberto Mangiagli later on in this conference. And LSST is going to cover the sky every 3 nights, going down to magnitude 24 in 30-second pointings, and with a large field of view of 10 square degrees. Okay, so let's see the idea. If you have the main idea, if you have LISA and Athena in the sky, is that LISA will start to see gravitational wave signal, and let's say the signal will enter in band way before merger, right? These things stay in band weeks, perhaps even months before merger. So that's very different from what we see with LIGO Virgo, where we catch only the last seconds or minutes of the signals. Okay, so you can start as the signal is accumulated, SNR grows, then you start to be able to locate the signal in the sky. And if your sky localization is good enough, you can point Athena in that direction, so that if there is a flare at merger or some rebrightening post merger, you can hopefully catch a distinctive signature of that. Can you do that? Can't you do that? Well, it's hard to tell. First of all, because we don't know exactly what the emission is. And second, because it's, sky localization with gravitational waves detector, as you know, is not that straightforward. And here you see, a pretty good system for sky localization, which is relatively light, is 300,000 solar mass black hole binary, a redshift, very, very close. So this is a very, very, optimistic case. So you see, for a system like this, already a month before merger, you have a sky localization within LSST capabilities. So you can really target that region of the sky every now and then with LSST to see whether over the weeks that are that you have before merger, there is some source that has some interesting periodicity that matches the evolution of the phase of the gravitational waves, for example. Okay. However, the signal enters in the Athena band only in the last 10 hours before merger, and that's bad because you cannot do gravitational wave data analysis for LISA in real time, right? You need to download the data from the satellite and process them. So you need to know where the system is, let's say a day in advance, and you can do that only for a fraction of those systems, right? However, if you consider the whole SNR accumulated in spiral merger and ring down as well, you get a sky localization that is much better. So you can always point Athena post-merger to see if there is a post-merger signature, like a X-ray rebrightening of your system, okay? Of course, it's hard to identify your source, to tell that that's the counterpart. So it's going to be much more complicated. But for post-merger signatures, actually, Athena and Lisa can do much better together, because in this plot, which is a bit complicated, essentially what you have to consider here is the thick black line, which is the overlap region for which, you know, if post-merger there is a source that have a luminon that has the properties of an AGN, let's say. Sorry. Can you see my slide?
No, we cannot see your screen anymore.
Yes, I know. I cannot see my screen either. And I don't know why is that.
Try to stop and share again.
Wow. Well, the problem is that I don't see anything. It's black. It became black. So I cannot unshare because I don't.
Okay, I can do it for you.
Okay, good. Oh, thanks.
Okay, go ahead now.
Okay, let's try again. Share screen. I don't. Okay, share. Wow, I don't know what. Wow, what was that? Okay. Thanks for solving the issue.
Oh, no problem. So anyway, you have 5 minutes. So I tell you my voice instead of writing.
Insert. Sorry, slideshow. How did I wait? How did?
Okay, I don't know. This thing I saw you also before this.
Okay.
This
okay, can you see that?
Okay.
Yeah, sorry about that. I don't know what happened. So essentially, these post-merger signatures. So assuming that your black hole is as a spectrum of a typical quasar, which is it's probably not going to be the case. So you can perform multi-messenger observation of post-merger systems with Lisa and Athena up to redshift 3, which is pretty much 1/5 of the observable volume of the universe. So there are good prospects of doing this. And of course, why you want to do multi-messenger? Because, well, you can do with these black holes up to high redshift, you can do cosmography with, beyond redshift 1 with astrophysical sources. You can study accretion physics on systems with known mass and spins that you can measure from gravitational wave observations. And you can study the interplay between gas and the massive black hole binary in the final stage of the merger, and so on and so forth. So that's very interesting to try to pin down those sources. So in my last 4 minutes, I want to talk a little bit about pulsar timing, which is actually another way to detect gravitational wave signals in the very low frequency band. And the idea here is that pulsars function as essentially perfect clocks, right? So you have these rotating stars that emit these beams of radio waves, and at each period, if this beam points toward the Earth, you can see you get the tick of the clock. Okay, so you have this perfect clock, and if there is a gravitational wave passing between you and the pulsar, this gravitational wave is going to squeeze and squash the space-time between you and the pulsar, and so these pulses are going to arrive a little bit earlier, a little bit later. Okay, of course, with pulsars timing, you are sensitive at very low frequency, so the massive black hole binaries are not in spiral emerging like in Lisa, like in LIGO Virgo. They are essentially monochromatic steady state sources. And you have, in fact, a superposition of them. You have many such binaries that build up a sort of stochastic signal. So I don't want to talk about this, though. I want just to point out that given the fact that this signal is dominated by the most massive system, and here you see the typical amplitude of the sources as a function of frequency, you might have several individual binaries that stick out of this stochastic signal, and you might resolve them individually. So you might have, several binaries that might be resolvable individually. Of course, it will take some time because we still didn't detect a stochastic background of gravitational waves with pulsar timing, even though there are some interesting common signals in our pulsars, but we still need to work a lot more on that. But in the real future, in the far, well, not so far future, we can actually try to detect individual sources with PTA. And then this is work that a former student of mine did. We can actually locate the pulsar the source in the sky with pulsar timing. And the sky localization is not great. It's going to be tens of square degrees. But since those signals, those individual binaries are produced necessarily by very massive nearby sources, you can actually cut off your potential counterparts, most of galaxies that are in your sky localization, and you can consider only you can rank the probability of your galaxy being the host of the source, and you can actually get down to, let's say, perhaps 100 or tens of potential hosts. And then you can actually monitor them and see, or look in the archival data, whether there is any interesting signature of a binary massive black hole in that galaxy, in those galaxies. And those signatures might be variable X-ray or UV continuum, double K alpha line if you have time to point Athena or whatever telescope there to see whether there are weird K alpha line in your system, and so on and so forth. So, for example, we make a study with another former student that in all sky we might have order of hundreds periodic binaries that are emitting in the PTA band that are within the reach of Universita. And Universita is going to survey the sky for 4 years. However, since the survey is very sparse, you will have not much points. You will have not so many points to build a light curve. So it's going to be hard to pin down those periodic binaries. Anyway, the future in PTA is going to be bright because we have Meerkat now that is observing, fast is discovering more and more pulsars, and eventually we'll have the SKA that is going to improve our sensitivity to these massive black hole binaries by an order of magnitude, essentially. All right, so I leave my conclusions there. Just want to remind you that low frequency gravitational wave band is going to be reach of sources and is becoming very interesting already in the PTI regime. And it's going to be a very exciting realm for doing joint gravitational wave and gravitational electromagnetic observations. So I leave you with that, and I take any question if there is any. Thanks.
Thanks a lot, Alberto, also for the timing. So are there any questions for Alberto? I don't see any, but I can start, and then let's see if someone else raises hand or her hand. So I saw that you talk about the radio for PTA, but you didn't talk about the radio explicitly for the electromagnetic counterpart of LISA detections.
Right.
I think there are some perspective also from the radio point of view there. Can you say something more? Which phases? I don't know, something like that. Which is
right. No, good. That's a good point as well. In fact, I just concentrated mostly on Athena because there is this active effort of the European Space Agency to fly the two missions together. Of course, in the radio we will have SKA by the time LISA fly, and essentially. With SKA as also, SKA, if you take SKA2, also the field of view is going to be of the order of several square degrees, and the sensitivity goes down to microjansky. So whatever type of radio jet, for example, that is going to be emitted at the merger or post-merger, if, oriented in the right direction, is going to be visible with SKA. Now it's going to be very hard because to pin down also this source in radio, but it's also true that the radio sky is relatively quiet in general. So if you have like something that pops up following a galaxy merger with SKA, that's certainly a very interesting prospect for investigation.
Okay, thank you. I see that there is a question by Luciano Rezzolla. Please, Luciano.
Hi, thank you, Alberto. It was a very nice review. Now, the question is about initial conditions for these binary mergers and the electromagnetic signal.
Right.
When I was looking into that about, almost 10 years ago, there was a lot of ignorance about what were the initial conditions. Essentially, people were simulating whatever they could simulate, not necessarily, what is in reality expected. Have things improved since then?
That's a very interesting question. So I would say not so much, in the sense that really, I mean, there has been improvements in numerical simulation in bridging the scales across of the binary evolution, right? And for example, I know that Marta is around. Marta did a lot of work in this respect, and she's doing a lot of work in this respect. And it's the hard thing is really to, as you said, to pin down what are going to be the conditions of the gas when the binary gets to sub-parsec scale. So to do that, you need to connect the different scale of the inflow of gas at high redshift, at large separation, at large scales, and then you have to zoom in to see what happens in the final merger stage by including all the relevant physical processes, including star formation and feedback and so on and so forth. So in general, it has been shown that it's likely, especially at high redshift, that there's going to be quite a bit of gas, cold gas around these systems. And those conditions have been used, conditions, let's say, inspired by this observation, has been used in several simulations to initialize, let's say, plausible circumbinary disks to massive black hole binaries. Now, the simulation of these last phases, the circumbinary disk and the binary, are always, are mostly very, very idealized, right? Most of them are 2D. You usually assume that there is a steady disk. There has been little work about checking what happens if you have gas flying and inflowing in different directions. So there is still a lot of work to do there to bridge the small scale to the large scale. But I would say that there has been, a bit of improvement in the last few years.
Okay, thank you.
So I see no other questions. Last chance. No. Okay, so I think we can really